Hey, geometry students. In this lesson, we are going to be taking a look at tangents and circles once again, and we're going to be defining a whole bunch of different terms related to tangents. But one of the most important statements in this entire lesson is right at the very top of the slide. Recall theorem 58.3, back from when we first talked about tangents in lesson 58. If two tangent segments are drawn to a circle from the same exterior point, so we have two segments that are tangents to the same circle, but at different points on the circle, they are congruent. Okay, that is a provable theorem, and it's going to play a central part in this lesson. So I want you to keep that in mind. I'm going to point that out again. If two tangent segments are drawn to the same exterior point and they're tangent to the same circle, that means that those segments are congruent. And if you can keep that in mind, not only will you do well on lesson 58 problems, but you'll do well on lesson 72 problems as well. Now, there are a couple of different tangent terms we need to get familiar with. We're going to start with these two on the right here. These are called exterior common tangents. Now, they're common tangents because they're tangents to different circles, but it's the same tangent line. Look at line N. That would be a common tangent to circle A and B. And line M is a common tangent to circles A and B as well. And here's the thing, for any set of two circles, you can draw two external common tangents. What makes them external? Well, there is no point at which these tangents pass in between the two circles. So I can draw a line from the center of circle A to the center of circle B without passing over the tangents. That makes them external. Internal tangents do pass between the circles. I can draw two internal tangents for any set of circles. And what they're going to be is a tangent. Notice that they're common tangents. They're a tangent to both of the circles. But I can't draw a line from the center of A to the center of circle B without passing through both of the tangents. That's what makes them internal. So they're common because they are tangent to both circles, and they're internal because they pass between the two circles. Then we can talk about circles that are actually tangent to each other. In other words, the circles intersect at just one point. We can have internally tangent circles where we have a circle inside another that touches at just one point, or externally tangent circles that touch at one point. And what we're going to find in problems that involve these kinds of circles, it's a whole bunch of figuring out where the radius is and where different radii are. And we'll know the length of the radius, and then you can just add different radii together to figure out lengths. Usually these are actually triangle problems. So you find lengths of different parts of triangles and then calculate different things related to triangles. So we're going to be dealing with this in just a little bit. Notice that letter B is an externally tangent circle problem where we need to find this length of the triangle. But wait, here is a radius of circle P and here is a radius of circle Q. And if we add them together, we get the hypotenuse of this triangle. Now, the other thing you'll need to pay attention to in problems like this is that if QR were a tangent to circle P, then we would know that this was a right angle, but we're not given that information. So pay attention to whether this is a tangent to this circle, because then you know you're dealing with a right triangle. Here, we do not know that we're dealing with a right triangle, so we're going to have to figure out what to do with that. All right. So we're going to get started on these problems here, and we're going to again focus on this theorem. If two tangent segments are drawn to a circle from the same exterior point, then they are congruent. In this diagram for letter A, it says that RT and QU are tangents to the circles. They're common tangents. They're internally common tangents. Find the lengths of RS, ST, and SU. RS, ST, SU. And I know that QS is 8. All right, now notice that here I have an external point, and then I have tangents drawn to the circle from that external point. So because of that, I know that SQ has to be congruent to SR, which means that SQ, which is 8, equals SR, which is x plus 3. I could solve for x. X equals, let's see, 5. And that means that the length of RS equals 8. Well, that was pretty obvious, though. I didn't really need to figure out X to figure out what this length was because I knew it was congruent to this length. RS equals 8. All right, but now that I have X, I can figure out the other sides, and that's what's important. So if I know that X equals 5, this looks like the easy one. 5 plus 8 is 13. Hey, let's just verify that that works for this one. 4 times 5 is 20, minus 7 is 13. So I know that ST equals SU, which equals 13. And that should be all that I need to know for letter A. Let's just double check and make sure I did everything right there. Boom, 8, 13, 13. Yes, so we got letter A correct. Let's move on to letter B. Now, letter B is maybe going to be a little bit harder. We need to determine the area of triangle PQR to the nearest square inch if circle P and circle Q are congruent tangent circles. Okay, so they're congruent circles with the same radius. The radii is 6 inches each. Well, here's what I know. PQ is drawn from the center of one to the center of the other, so it's 2 radii long. That means that PQ is 12 inches. I also know that PR is 6 inches. But that PR value in and of itself might not be helpful because it's not perpendicular to the base. If this was the base of the triangle, um, that doesn't necessarily help me because this needs, in order to find the area, I need to multiply the base times the altitude, which is perpendicular to the base. So what I need to do is figure out what this altitude here is. Okay, so through the magic of video, I've actually been spending a lot of time on this that you didn't have to watch me. And what I discovered is that there's just not enough information given in this problem. They missed an important detail. QR is a tangent to circle P. It has to be. Otherwise, you wouldn't be able to solve this. So, in most of the time, this problem is going to say QR is tangent to circle P, and then you'll know that this is a right angle. If this is a right triangle and we know two sides of the right triangle, we can find the third side of the right triangle. And then if we make this our base, PR our base, then RQ is automatically perpendicular to it because it's a right triangle, and I can do 1/2 times this length times this length. So how am I going to figure that out? Well, I know that 6 squared plus whatever QR is squared equals 12 squared. And I'm going to figure out what this is using a calculator. So what we're going to do is, I know 12 squared is 144 minus, and it was 6 squared, so minus 36 gives me 108. I need the square root of that number, of 108, and that gives me a side length of 10.4. Okay, so that means that my QR equals 10.4. And now what I'm going to do is QR times PR. So 10.4 times 6 times 1/2. And that will give me the, let's see, 31.17 says round to the nearest whole. So it's just going to be 31. So my answer is 31 inches squared. Let's see if we did this one right. There we are. So they left out a crucial bit of information. All right, on to letter C. All right, let's go and revisit for a moment this Theorem 58.3. If two tangent segments are drawn to a circle from the same exterior point, then they are congruent. Now let's take a look in letter C. A system of pulleys is set up as shown. Here we have A being a common exterior point, connecting B and D, which are tangents of the smaller pulley or the smaller circle, and C and E, which are tangent points of the larger circle. Notice that there's a common tangent between these two circles on top, common exterior tangent there, and a common exterior tangent here, external. So we see that we've got these tangents here. Now let's just consider what this theorem means for this. AC has to be congruent to AE by theorem 58.3. So does AB and AD. So if these two lengths are the same, And these two lengths are the same. Does it make sense that this long length minus this short length equals this long length minus this short length? And because I'm subtracting the short length from both of them, I could just ignore the short length altogether and say that this 19 has to be congruent to 5x minus 6. Whenever you have external common tangents like this, and remember, there's always two external common tangents that can be drawn between two circles. Well, that means that these external common tangents are always going to be congruent to each other. Now, there's no theorem that states that, but it's pretty easy to prove from theorem 58.3. So what does that mean for this problem? 19 equals 5x minus 6. We're going to add 6 to both sides, and we're going to end up with 25 equals 5x, or x equals 5. Okay, and that is how you work these types of problems. You should go ahead and work the problem set for next time.